For the kind introduction, and thanks all the organizers for having me here today. Today I'm going to talk about some recent work on generative diffusion models from the aspect of optimization, generalization, and fine-tuning. And this talk is based on two papers. The first paper is neural network-based score estimation in diffusion models, which was published at iClear in 2024. And the second paper is stochastic control for fine-tuning diffusion models. We talked about optimality, regularity, and the convergence of the algorithm. Both papers are based on joint work with my former colleague Mason and our student Yinbing. So feel free to chime in anytime if you have any comments or questions. I would like to make the session interactive. Let's take a look at the evolution of generative AI first. If we look at the history of all the architectures we heard a lot recently, the history is actually not very long. The first noticeable architecture variational autoencoder was proposed in around 13 years ago at 2020 and 2012. And then generative adversarial network attracts a lot of attention due to its powerful performance in generating high quality images. And then Transformer came in the past 5 years. We've seen a lot of successful applications at large scale. For example, the ChatGPT that we all use for daily work and life, and also DALL-E 3 for video generations and etc. So this huge wave of generative AI have changed a lot of things at work. And I believe that there will be more exciting applications in the vertical stream in all different kind of applications that we'll see in the next few years. Today, I will focus on one specific generative AI architecture, which is called diffusion models. For diffusion models, we've seen successful applications in image generation, speech synthesis, and also in science, such as protein folding and structure generation. There's a lot of promises of using diffusion models to sample protein conformations, as well as DNA, RNA sequences. And there's also applications in using diffusion models for medical image reconstructions. I work a lot on financial applications. We've also seen promises there of using diffusion models to simulate high-dimensional asset returns, time series, and also other type of financial scenarios, such as volatility surfaces, and also link model book dynamics, which is on the micro level. And of course, there would be many other applications that diffusion model is capable of working on. With these promises, I want to talk about why diffusion model is so popular in generating different type of data, and what's the mathematical foundation behind it, and what are the interesting scientific problems we can look into. So this would be the outline of my presentation today. I'll first briefly introduce the idea behind diffusion models and set up the notations. Then I will talk about the first paper I mentioned on optimization and generalization guarantee. Then we can talk about post-training, specifically the fine-tuning using stochastic control aspect. So the idea behind a generative diffusion model is really simple and elegant. If we consider a forward dynamic driven by a stochastic differential equation with a drift term B, which is time-dependent, state-dependent, and a simple volatility term that is only a function of time t. And we start with the initial position x0, a sample from the data set. Then we can gradually add noise to our initial data. We can think about x0 as an image from the data set. We gradually add noise to this image according to this differential equation. Then when time moves on, the picture will get more and more blurred. At certain time capital T, the picture will just look like a white noise. If we denote this PT as the marginal distribution of this process, then if we can find a time reverse SDE of the forward process that we use to add noise, then we can slowly denoise starting from a sample x0 bar from this P capital T distribution. If we can do a time reverse SDE, then at time capital T, we will be able to get a new sample from the ideal distribution P data because the forward process and the time reverse SDE shares the same marginal law. Then the nice thing about this forward and time reverse process is that for the forward process, it's driven by a Brownian motion BT, high-dimensional Brownian motion BT, but the time reverse version is driven by a different Brownian motion that is independent. In such a design, under such a design, x capital T bar will be different from where we start from, but it follows the ideal distribution that we want. That means we can get a new sample that is different from the data set we have, but it follows the ideal distribution that we want. Okay, so two comments before I talk. I go into details about the time reverse SDE. The first comment is that usually we will choose the sampling horizon T to be sufficiently big, so at time capital T, the image looks like a white noise, so that if P capital T, the marginal law, is different to simulate, we can approximate this by a Gaussian distribution. And the second comment is that intuitively, it should be easy for this time reverse SDE to guarantee generalization or sample diversity because we can simulate as many independent Brownian motion as we want to guarantee that the simulation procedure has enough diverse noise so that we generate something different. So these are two comments. So the magic is, what does this time reverse SDE look like? Is it easy to sample? Is it well-defined? Okay, we actually have the answer from the stochastic analysis literature in the 90s. If we denote PT as the marginal density of the forward process xt, then if we define a new process in this diamond equation, so dxt bar, the xt bar process is driven by the drift term b bar and volatility term sigma bar. And then under very mild conditions, we can show that this diamond equation admits a strong solution and xt bar has the same marginal law as our forward process with the time reverse. So the volatility term is simple. It's just the time reverse version of our volatility term of the forward process. The drift term is a bit more involved. It has two terms. The first term is the time reverse of the original drift term, and there's a correction term, which in the statistical literature is called Stein's score function. So we have this sigma square in front, and here, this is a bit hectic. This is the gradient of a log density function, okay? So we need to know the marginal law of the forward process in order to specify the drift term. But once we specify the drift term, we can approximate the drift term, then we are able to simulate according to this new differential equation to get new data from the noise distribution. Okay, so that's the idea behind the design. Okay. We know that because we can design the forward process to add noise to our data sets, so we know the drift term B and we know the volatility term sigma. The hectic part is the density function P, because if we don't know the data distribution P data, which is the initial distribution that we get sample from, then we won't be able to know the marginal loss. That means if we can learn this gradient log P, the Stein score function, good enough, then we are able to get an approximated version to this time reverse SDE, which can help us to simulate more data. Okay. So the learning part comes in order to approximate the unknown term in the drift B bar. Okay. So there are a few methods in the literature to approximate the gradient of log p, which is called score matching, we want to specify a functional class, usually the parametric one. For example, we can think about a neural network with parameter theta, so that would be our S theta. And we want to use all the available data in our data sets to minimize this score matching error. We want to find the best possible S theta within our specified functional class so that S theta is a good approximator to the gradient of log p. Then we can plug S theta back into this B bar term, replacing the unknown Stein score function, and use this as an approximator to B bar and then simulate new samples. So that would be the idea. So for the input of this loss function, we sample x0 from the data set, and then the conditional law of xt given x0 follows the forward SDE we specify. Sometimes we can even get a closed form for xt, and then we use xt as the input to many xt's as the input to the loss function. And another comment I want to make is that t is also an input to this function because we need good estimation of the Stein score function at any time t in order to follow the right trajectory to recover the data that we want to simulate from. Okay, so t is a very important input to this functional class neural network architecture, for example. So these are the important ingredients of the generative diffusion model. First ingredient is that we need to have certain knowledge about the time reverse SDE. And the second ingredient is that for the quantities that we don't know in the time reverse SDE, we want to design a loss function to learn the unknown functions in the time reverse SDE and then use the approximated version to sample data, new data. Okay. So that would be the high-level idea. Before talking about some developments in the literature, I'll pause here to see if there's any comments or questions about the idea behind diffusion models. Okay, if no, let me continue. So if we want to touch a bit on the theoretical foundation of diffusion models, we can think about where can the error come from. So if we compare the data distribution, which is something we don't know, but we want to get more samples from, versus the output distribution from our time reverse SDE under the score approximator, then errors appear at several different levels. First of all, because we use S theta to approximate the Stein score function, then there would be score approximation errors. The second error comes from approximation error of the terminal density function, because as I mentioned, P capital T is something we don't know. So when we run the time reverse SDE, most of the time we'll replace P capital T by something that is easy to simulate from, for example, high-dimensional Gaussian process. And also sometimes even we know P capital T, it would be difficult to sample from the exact distribution. So usually we replace this P capital T by something that is easy to simulate from, and we need to make sure that this error on the terminal distribution won't explode while we do the simulation along the time reverse SDE. So there's approximation error to the terminal density. And of course, if we want to simulate an SDE in practice, we need to do discretization in time. And we want to make sure that the discretization, when we implement the time reverse process, is also well controlled. And if we look at how these errors, different level of errors contribute to the mismatch between P data and log of X bar, there are some very nice results in the past 2 years. They have slightly different assumptions on how the target data distribution look like. For example, is it a data distribution on a bounded domain, or how fast the tail decays if it's defined on an unbounded domain. So they have slightly different assumptions. But if we summarize all these nice results, usually we can upper bound the total variation of the output law versus the data distribution by 3 terms. So we can see that the noise inaccuracy has an exponential decay in the sampling horizon here. But the score mismatch error has a polynomial dependence in T and also the time discretization. So that means if score mismatch contributes to a huge level of error, then we won't be able to have a good control on the output law of xt bar compared to the data distribution. So that's one of the motivation when we first started studying diffusion models. We want to find or design a good optimization algorithm that people can implement and think about what type of architecture we want to use to approximate S theta so that we can guarantee a low score mismatch error. Okay, because for the first part, the noise inaccuracy, when we replace PT by high-dimensional Gaussian, we see that this decays exponentially fast as long as we specify a good class of forward process. And in terms of the error dependence on the discretization, this is a well-studied subject in numerical SDE. So that's why we also refer the results to the literature for the third part, and we focus on investigating the score mismatch error because this is something new from the diffusion model design. Okay. Yeah, this is the main motivation when we started looking into this problem 2 years ago. So I'll talk about the optimization and generalization guarantee to guarantee a small mismatch, score mismatch error. So in practice, the high-level idea is that we always want to simulate more data, which is x0 for the forward process using the notation we just established. And in order to simulate more realistic x0, we need to find a good functional approximator to the gradient of log p. And if we approximate gradient of log p directly, this is called explicit score matching. People realize that if we approximate this gradient of log pt directly, then sometimes it's very challenging and difficult in practice because p0 is unknown, then we don't even know the target function that we want to approximate. So that's the challenging part people realize. Then what has been developed in the literature is that then how about we decompose the gradient of log p and somehow learn the denoising score function, because condition on what happens at time 0, we know the conditional transition law because that's determined by how we specify the forward process. So instead of using explicit score function, there's a lot of success of using denoising score function to decompose the gradient log p to have an objective function that is accessible to us. And using this conditional score function makes the estimation easy to implement, and it has very good performance in practice. But this route of looking at the conditional version of the Stein's score function doesn't really help in terms of, it works very well in practice, but it doesn't help us to build an optimization foundation. So we realized that, in order to say something from the optimization aspect and build a theoretical foundation, we need to take another route and look at this conditional expectation of x0 given xt. So if I run the forward process for some time up to time small t, then I observe xt, I want to know what would be my conditional expectation of my initial position xt given my current position, initial position x0 given my current position xt. We realize that if we define this quantity as f star tx, And then we can use results in the nonlinear regression literature with noisy label because the initial data x0 can actually serve as an approximator to this f star function that we want to approximate. And this view of studying this intermediate quantity f star gives us a nice perspective to borrow results from the statistical literature to help us build up this foundation. And the connection between this posterior mean and the Stein score function, we can get it via Tweedy's formula, which is also something classic in the probability literature for certain class of SDEs. And I will talk about this in a bit. So by borrowing this intermediate quantity f star, it helps us to build up the optimization foundation and borrow results in the literature of nonlinear regression. Okay. So this is essentially the route we take to build up the optimization foundation. To be a more concrete, let's focus on a simple time-varying Ornstein-Uhlenbeck process. So this would be the drift term BT we work with. So it's a time-varying linear function here. And also the volatility term is also simple, square root of GT. GT is a non-negative function of time t. And by applying Tweedy's formula, we can see that Stein score function is just a linear combination of f star and something we know because GT is also a function, HT is also a function of GT. So that means, oh, this Stein score function has a very nice connection to the intermediate quantity that we want to investigate. So all the focus can be translated to approximate this posterior mean. Okay, and statistical wise, there are studies that can help us to do that once we build up this connection. But this doesn't hold true for very general SDEs, or I'll put it that way. So for more general SDEs, if we apply Tweedy's formula, the result we get will be more evolving. And the analysis we have heavily relies on this linear relationship between gradient log P and F star. So what happens with more general SDEs, I think is still an open problem because many developments in the literature heavily relies on this simple format of OU process, which works well in practice, but I want to make this comment. So in our setting, once we focus on this Ornstein-Uhlenbeck process and applying Tweedy's formula, the score matching objective function for us becomes the following. So instead of approximating gradient log P, we can approximate this posterior mean as our objective function. And so this is much easier to work with because F star has a simpler meaning, but still, in this objective function, as theta is a neural network, we specify, or a function in a functional class we specify, but we still don't know the objective function. The target function f star is still unknown. What we realize is that we can establish an equivalence to the star objective function. So if we replace f star by the noisy label, which is just the data sample from our data set, then these two problems has the same minimizer in terms of the functional class we specify. And this is way easier to work with. So what I meant is that if we replace f star by x0, then these two problems have the same minimizer. And this helps a lot because x0 is something we can access from the data set. So the target function would be something we can observe. And another nice thing is that this noisy label x0 can be served as a noisy label of the true posterior mean that we want to approximate. And a more involving thing is just that epsilon is not an independent noise that people typically use in the linear regression literature because it does depends on both xt and x0, but we have a nice view to move forward once we make this identification. So what we have now is that we have a nonlinear regression with a noisy label. Okay. So what we want to do is that if we are interested in training a neural network to approximate the score function, then can we use the simplest thing we can think of and then see what will happen? Can we get something from a theoretical aspect? So the parameterization is also simple, two-layer fully connected neural network and with ReLU activation function to serve as the approximated score function. And then we want the neural network to minimize the empirical loss function. And we have n samples in total in our data set. So this would be our objective function. And the initial data serves as a noisy label to help us train the neural network. So very simple architecture and the classic empirical risk minimization problem. And when we train the neural network parameter theta, we use gradient descent algorithm, no batch update, no stochastic version, just the simplest thing we can think about. Okay, so we take gradient with respect to the empirical loss function to update the parameter. So how good this algorithm is in terms of the theoretical result? So what we can show in the 2024 paper is that if we are in the over-parameterization regime, in the sense that this two-layer neural network is sufficiently wide, then if we train the neural network by gradient descent and consider a certain type of early stopping, then with high probability, we can show that the Stein's score, our approximated score function is close enough to the true Stein score function, and the error in terms of the dependence to the sample size is on this order. So D is the dimension of the data. Okay, so this is the first result on the generalization error of gradient descent type of algorithm for neural network. The reason I mentioned a generalization error is because we see in the training we do gradient descent for the neural network parameter using the empirical loss function using n samples. So the neural network only see these n samples. But when we do the evaluation, for example, how good our trained score function is, we evaluate that on the population level. So this is evaluated under the true data distribution, which is unknown. So this is the generalization error. That means if we train the score function using n samples, it generalizes well on the entire population. So we don't need to worry about overfitting because we have guarantee on generalization at the population level. And another comment I want to make on the result is that this result achieves the minimax optimal rate. The order is minimax optimal. It matches the results for non-parametric regression. So essentially, if we don't further specify the structure, geometry structure of the data sets, then this would be the best we can do. Another comment is that if we think about image, the dimension D would be huge. So there are some recent studies on taking closer look at the data architecture. For example, does my data has any low dimensional property, manifold structure, so that people can use that structure in the data to further reduce the curse of dimensionality here. But without further assumptions on data, this would be the best result one can expect. One thing I want to mention in terms of the techniques we used in the proof is that essentially in the over-parameterized regime, when the width of the neural network is sufficiently wide, then neural network training would be equivalent to kernel regression in a good RKHS. And this would be the perspective we use in the proof, and I'll mention the high-level idea on the next slides. Another comment I want to make is that early stopping in terms of the training of neural network. So tau would be the number of iteration we take on training neural network. Having an early stopping on tau instead of letting the algorithm run for too long actually helps a lot for us to balance the variance and bias. This is because we don't have the exact data label that we want. We don't have access to F star if we only have a noisy version of the label to prevent the algorithm to overfit to label noise. The early stopping actually helps a lot. So that's another comment I want to make. So in terms of the details of the proof, in order to control the gap between the target function and the output of the neural network, we upper bound this error term by 4 terms. The first one is the truncation error, because most of the optimization techniques and statistical techniques work on the bounded domain, but diffusion models diffusion processes are unbounded, but with high probability it's bounded in a large ball. So we use a truncation error here with a sufficiently large radius, and then we work with a RKHS functional class, and then which is nice enough, smooth, and with very good control on the approximation power. And this approximation gap would be the best function in the RKHX we specify to the target function. Okay, so this arrow is controlled by the richness of the functional class we specify. And within this functional class, we couple the neural network with the neural tangent kernel, and this would be based on the design. I'll show that in a bit. So essentially, on the implementation level, we'll implement a neural network. But in the analysis level, we will couple a neural network with a neural tangent kernel, so that nonlinear regression literature helps a lot. And then in the level of analysis, we analyze the corresponding neural tangent kernel to see how close our trained neural tangent kernel can get close to the best approximator in the functional class we specify. And when we try to bound the best approximator versus the evolution of the neural tangent kernel, early stopping in terms of the iteration number helps a lot to control the last term. So we control these 4 terms separately in order to get this minimax optimal rate. So that would be the high-level results. The idea is to build a connection to the neural tangent kernel and then try to use the results in the statistical literature to control the error term. Okay. A final comment I want to make here on the training of neural network is the following. So we work with the RKHS, reproducing kernel Hilbert space induced by the neural tangent kernel in the following format. So we can see that the way we specify the kernels really depends on the neural network, because this AI coefficients and the theta 1 would be the initialization of our neural network, and AIs are the weights. Let me see if I specified that. So I didn't do that. So AIs would be the weights on how we connect these neurons in the hidden layer. So it's we don't train AI, but it's part of the design of the neural network. So we can see that how we specify the neural tangent kernel really depends on the neural network architecture. So we couple the neural tangent kernel with the neural network in a very specific way so that we can control the closeness of our neural network at iteration tau and the kernel predictor at iteration tau. So we couple them to make sure that they stay close enough with each other. And the closeness between these 2 approximators is controlled by the weight of the neural network. So M would be the weight of my neural network. And this is actually consistent with the intuition in the literature that when the weight of the neural network goes to infinity, gradient descent with neural network with the over-parameterized neural network is equivalent to running a regression method using the corresponding kernels. Okay, so the difficulty of these two problems or the hardness would be equivalent, and this is also the perspective we take for analyzing the diffusion models. So the final comment I want to make here is that the theoretical finding we have is also consistent with some very recent empirical findings in the literature. So I made a brief comment that the perspective we take in analyzing the optimization guarantee is that we view x0 as the noisy label to the posterior mean that we don't know. And of course, by making this observation, we also have label noise here. So that means for diffusion model problems, label noise is something inevitable. It comes with the nature of the problem, and we do need to have early stopping to prevent the neural network to overfit to label noise. Because in the end, what we want to approximate is not the input data, but the posterior mean, because that's the function that we want to approximate. So early stopping, theoretically, early stopping help us to bound the difference of the last term. And empirically, we also find that early stopping is very important when we run the experiments. For example, in this 2024 paper, they mentioned that diffusion models learn data distribution with generalization first, and then the model starts to memorize if we don't do early stopping. So which implies that early stopping is very necessary and essential for practical implementation. And we also observe that theoretically, if we want to have a good control, early stopping is also important. So the theory we find is consistent with many interesting empirical findings in the literature. So I'll conclude with some numerical examples. As I mentioned, if we don't further specify the data structure, it suffers from a curse of dimensionality if we look at this result. But we do want to provide some numerical insights exactly using what we proposed, although it's very simple, to shallow neural network with gradient descent, no fancy modifications. So we choose to work with a very simple data set, which is tabular financial data. We have this credit default data set publicly available. So it contains bill statements of credit card customers, history payment, default payment, and some demographic information in Taiwan in 2005. And we trained our two-layer neural network gradient descent method on this data set, and we compared the results with the state-of-the-art architecture, which is called FinDiff, financial diffusion models. So in this paper, they proposed two types of fidelity, column fidelity and row fidelity. The higher the fidelity is, the more the generated data, the more realistic the generated data is. So we can see that although our method with two-layer neural network with gradient descent doesn't beat the performance of the state-of-the-art result, but it gets very close. Remember that FinDiff is a very sophisticated design, and for us, we just use the simplest thing we can think about, which is consistent with the theoretical framework. We get very good results, actually, which means the key takeaway here is that simple architecture really works well. As long as you implement the early stopping in a proper way, it gives us very robust result, at least on this small size data set, and it's very easy to train. Gradient descent, nothing more. Okay, so this would be a main takeaway if we implement what we proposed in a small scale data set. Okay, so I think I'll take another pause to see if there's any questions for the first part before I move on to briefly mention about fine-tuning. I think I probably take too much time for the first part, but I still want to see if there's any questions before I move on.
Do I have a quick questions? So
Yes,
what is
please.
the criteria of the early stopping used
Mhm,
in
mhm.
your experiment?
So that's a good one. The early stopping we take is actually evaluated with the neural network. So we look at the we look at the we essentially we look at the evolution of theta tau and then decide whether we want to stop here or not. So we look at the dynamics or trajectory of theta tau and then decide whether we want to stop now or not. So it depends on some second order approximator constructed using as a theta using theta, but a short answer is we only need theta to determine whether we want to stop or not.
Okay. Yeah. Thank you.
I have another question.
Please,
It's about the inequality presented on the another page, I think.
uh,
Uh,
this page.
yeah, this one.
Mhm,
So you
mhm.
mentioned that you need to do this sort of truncation in order to control the bounds. So does it mean that this entire inequality doesn't hold almost surely? It holds like with high probability since you can, so it might explode, just.
Yes. So for OU process, because OU process mean reverting, then you can show that with high probability, the process will stay within the ball of radius r with high probability. And also as a consequence, all the results we have are high probability sense. So with high probability, this expectation is on the order of 1 over square root of m, and as well as the final result is always the high probability sense.
Oh, yeah, that clarifies it a lot. Thank you. And also, for the early stopping, it kind of contributes mainly to the last term, right?
Yes, yes, yes. When we want to control the neural tangent kernel at iteration tau versus the best approximator one can ever find within the class of function we specify, we do need early stopping because it decreases first, it gets closer to the best approximator, and then it starts to diverge and overfit to label noise.
Okay, thank you very much.
Okay, then let me continue. So I don't think I have much time, but I do want to mention a bit on the second part, because I think from an academic perspective, there are many interesting things one can study at the post-training phase, not at the pre-training phase, because I think pre-training phase, many big tech companies, they have a lot of computational power to make it with extremely good performance. But from an academic perspective, sometimes we have more domain knowledge for certain applications and more understanding of certain data sets. So there are many interesting fine-tuning problems one we can look into, and computationally it doesn't take a lot of resources to make it a good performance. And there are many interesting post-training questions one can look into. I just focus on fine tuning because I have a background in stochastic control. And while I introduce the problem, you will see that it has a very nice and cute connection to stochastic control and reinforcement learning. People also use reinforcement learning to fine tune if we have a human preference. So it's all related. So fine-tuning of the diffusion model studies the following problem. If we have a pre-trained diffusion model, say that I already have a good functional approximator, a neural network, to the Stein score function, then I want to do something further. I want to incorporate some individual preferences. For example, I have a very specific preference on the style of the content, and or I want to adapt my current simulator to a specific downstream task. How can I do this minor modification in a efficient way. Meanwhile, we can have some guarantee on the efficiency of this adaptation. One example is this Google Stream Booth. If I have a lot of input image of dogs, and my personal preference is that I want to have an image of my dog in very different scenario, in Greek or in a scenario that someone is giving the dog a haircut, things like that, then how should we adapt a pre-trained diffusion model with certain individual preference? What's the most efficient way? What's the principled design to achieve this minor modification or fine-tuning or guidance? People use these words for this type of tasks. So how should we do that? Mathematically, we need to formulate that as a optimization problem that we can write down. So let's think about what would be the objective function if we want to formulate this fine-tuning problem. First of all, these fine-tuning problems usually comes with a human preference or a reward function. So if on the left is the output of our diffusion model, well-trained diffusion model without fine-tuning reward function, then think about this as the output distribution. Then we do have a non-negligible mass that corresponds to the low average reward regime, as the reward is specified by someone. So the first thing we want to do is that we want to shift the distribution so that we have more mass concentrated in the high reward domain or high reward area. If we think about, because for diffusion models, the sample is simulated according to the time reverse SDE. So a natural thing to do is to add another drift term f so that it drives the entire dynamics towards high reward regime. So the first thing is, can we add an additive drift term f, which is the simplest thing one can think of in order to modify the dynamics, modify the simulation procedure according to an SDE. Can we modify the drift a little bit so it guides us to simulate more data in this high reward regime? So this is the first ingredient we want to do. We want to add a drift term so that we simulate more data according to the high reward area. Okay. Another objective function we also want to consider is the fidelity, because reward function is specified in a very simple way. I want this style, I want that style, I want my dog to be in a certain region or doing certain things in a certain scenario. So reward is usually specified in a very simple way. And sometimes if we optimize the reward function, then we satisfy the data fidelity. For example, if we look at this image from the very nice paper by Yohara and his co-authors, we can see that there would be scenario we see on the top line. The rewards of the images are very high, but it doesn't correspond to the context we want to simulate, because independent of whether we want to simulate snail or octopus or cheetah, it always gives us the same thing. It has a high reward, but it doesn't generate realistic or meaningful contents. But on the other hand, if we look at the second row of the image, they all have high rewards, but they simulate contents that we really want. So on one hand, we do want to optimize over the reward function, but on the other hand, we also want to preserve the data fidelity. We want to make sure that we are simulating something that is meaningful. Okay, so in order to balance these two aspects, one is optimizing over reward, the other one is preserving fidelity. What would be a good mathematical framework to take care of both? What we realize is that stochastic control or reinforcement learning is actually a very natural fit to balance these two objective functions. So for example, if we take a pre-trained model, usually a pre-trained model is something that is already implemented. So we use the discrete time notion instead of continuous time version. So so consider that we already have a pre-trained model that can help us to go from the noise, which is the initial position of the time reverse SDE, to a data, and we consider the denoising diffusion probabilistic models, which is consistent with the Ornstein-Uhlenbeck process we specified for the first part. So this would be the dynamics. We focus for the fine-tuning. We assume that this is already given. We have a very good pre-trained model that can help us to simulate samples that is very close to the ideal data distribution we have, and the fine-tuning problem can be formulated as the following. So in terms of the dynamics, the only difference is that we replace this pre-trained score function by a control. Okay, so if we want to, this controlled dynamics is with respect to the following objective function. So for this control problem, the objective function has two parts. One is the reward optimization part, because we want the output data to be able to maximize the reward function. We want the data to collect high reward, but on the other hand, we want to maintain data fidelity, as I explained in the motivating example. The natural way to maintain data fidelity is to make sure that, the transition kernel at each time t of my new dynamics stays close to the transition kernel of the pre-trained model. So I want my new dynamics to stay close to the pre-trained model, because this pre-trained model is usually trained with a lot of data with very good performance. So we want to utilize the good performance in the pre-trained model as well. So we want the dynamics, the new dynamics, to stay close to the original one in the sense of the transition kernel with the KL matrix. So this is what we have, and we can balance these two objective functions using this hyperparameter beta. Okay, so with this, so we can see that this is a special case of the general stochastic control framework one usually consider, because the dynamics depends linearly on the control UT here. And if we take a closer look at this KL function, it can be written as a quadratic loss function on the difference between control and my pre-trained score function. So it really has a very nice structure. So it's a control problem that takes care of the key characters of this fine-tuning downstream task. So we can say a lot about the efficient design of this type of control problems. I think I don't have too much time to talk about this part. One thing I want to quickly mention is that stochastic control and RL has been used in the literature to study fine-tuning problem, but there's no convergence result that has been established in the literature because most of the existing algorithms are very generic RLs that you can find. It doesn't fully exploit the structural property I just mentioned, for example, linear dynamics, and also the once we rewrite the KL divergence, it gives us a square loss on the difference between the control and the pre-trained score function. We are able to show a linear convergence rate of an algorithm by fully utilizing the key properties of this specific application. I think I'll skip all of these parts. This is on the property of the value function, and there's a nice semi-explicit form of the optimal control. We can see that the control is just optimal control is the minor adjustment to the score function, and this adjustment, fine-tuning adjustment, takes care of the reward signal, and it also depends on the trade-off beta we specify. We can show that if we use the iterative policy iteration algorithm, both the control and the gradient of value function has a linear convergence rate to the optimal one. And one challenge is that we need to show theoretically the regularity is maintained throughout training, which is non-trivial at all, which is the key thing we established in the paper, but I'll skip that. So we also have a very good performance of the proposed algorithm when we compare with the method implemented in the literature. I'll skip that part. If you're interested, we posted the code on GitHub, so you can take a look and play around with the algorithm you are interested. So I think I'll stop here. I take too much time on these two projects.